So the other person wanted to record. Now I have powers to record. That's why Mr. Sendal was taking me back. So the first instrument I'm going to talk about that detects radiation is the instrument which is called the GM tube. Which some of us call the Geiger tube. If someone's reading the chat, who is that one? Unassigned. A young Precious is in which class? Is she in the physics class?
Yes, teacher.
A young Precious, is she in our class?
Yes.
At any call. Okay, I have to join them. Now, this device is made up of a thin mica window. These guys are late. The thin mica window looks like this. Then it has a metal casing. Then it has a thin wire anode. Then even Nachijoba is in our class. No, she's in May. I think she's going for geography. So this goes to the amplifier that amplifies the pulses. So this is the metal cathode. This is what we call the thin wire anode. There are other illustrations which books have. You'll find an illustration of this kind, which is something like this. Ideally predicting the same. Then we have our thin wire anode right there. Then we have these other illustrations, ideally similar. So if you land on such an illustration, it is the same as the one I've drawn up. So those are the same illustrations. So this still would be our thin wire anode. This would be our thin mica window. Which is the same as the one up there. Then there is a gas in here. That is argon. plus a halogen vapor. This is a resistor. You know the wire anode is positively charged, so it's coming from a positive terminal. That's why this is joined to come and bring this thin wire anode right there. Now, what happens is we put a radioactive source in front of the thin mica window. So this is a radioactive source. Radioactive source.
You have seen these ones are true. These ones are really wanting to therefore make I'll give question to have the following.
Please giving us that second. Issues are girls, co-host mute. So having realized that, let me first convert my name. So that is how the Geiger tube looks like. If that is how the Geiger tube looks like, now we need to understand how it operates. Of course, this part is aft, just like the one up there. And we all know that this is a capacitor, not a battery, but a capacitor. So the experiment is working, the diagram is working, and if it's working, you are awarded at least maximum of 2 marks for a correct diagram. Now, with that note, this one is assigned to, and so the structure consists of a metal cathode in form of a cylinder. So that metal cathode is cylindrical. Sometimes we call it a cylindrical cathode. This shape you're seeing, the whole of it is a cathode, that casing. And a coaxial wire anode, a thin wire anode, which is here. Sometimes they ask you a question, explain why the anode is made of a thin wire. Then the spaces between the electrodes, we insert there a gas such as argon. So the space between the anode and the cathode, so this space, all of that space, that is why I told you this line was going down here. It is the same as this space here. That space has got argon plus a halogen vapor or neon. It can even have neon. Then the thin mica window allows easy entry of the ionizing particles or radiations from the source into the tube. Then the argon vapor the argon gas at a low pressure is used to form ions or ion pairs when the ionizing particles collide with the gas. Now, in that sense, what does that mean? That should tell you that if the radioactive particles enter into the chamber or into the cylindrical metal cathode here, when they enter, what is going to happen? They are going to collide with the gas molecules, which they are going to find in there. When they collide with the gas molecules, what is going to happen? They are going to form ion pairs. When ion pairs are formed, the different ions formed move to their respective electrodes. For example, if we know very well that electrons maybe are green and they have reached here and they have collided, the electrons will come and try to concentrate on the thin wire anode. Then the positive ions will tend to go to the metal cathode, which was negative. So let me call this P. So the positive ions have moved to the metal cathode. So when does this happen? It happens when the radioactive source enters into through the thin maker window and enters into the GM tube. When it enters into the GM tube, the reactive source is going to find their argon gas, and the reactive source particles are going to collide with these argon gas molecules. When they collide, what happens? They form ion pairs. The ion pairs formed move to their respective electrodes. Now, some of you want to write out. You will say the electrons move to the anode, and then the positive ions move to the cathode. When a physicist who is summarizing and is writing an exam says the respective ions move to their corresponding electrodes, or the ions move to their respective electrodes, you have summarized that in one simple statement. So when you're writing in an exam, you better summarize it in two ions moving to their respective electrodes. Owol Abba, what combination does she offer? And number Jomas 2.
Not physics.
But I don't know where, I have to assign them classes, but I don't know which classes to assign them. Now, I was still telling you what happens exactly before I give you the general write-up of what it means, what to have to write. So, you will discover that after these electrons, how do they go to their respective electrodes? They travel, or they're accelerated very fast to their respective electrodes by the high PD between the anode and the cathode. Okay? So, what happens is there is a discharge between the anode and the cathode, and that discharge brings about a current that flows through the resistor and produces a PD that is amplified to the retimeter. There is a retimeter that side, and then it is passed through a counter which registers it, or which registers that there is presence of ionizing particles or radiation through the what? Through the tube. Now, there are some key items which happen here. One, we get what we call an avalanche of electrons. An avalanche of electrons is what we call, it's an electron cloud. Yeah? So the whole of this one you see is called an avalanche of electrons. When we have a cluster of electrons on the ions, we shall form what we call an avalanche of electrons. So they can ask you, define what an avalanche is as applied to the GM tube. An avalanche is an electron cloud. An avalanche is an electron cloud formed on the thin wire anode of the GM tube. Okay? So if it's an electron cloud, it means you have a clustered group of electrons somewhere. So they form what we call an avalanche of what? Of electrons. So that is a definition you should have or to note. Another definition is what they call a halogen vapor. Halogen vapor,
Pardon.
an avalanche of electrons, is a cloud of electrons formed on the thin wire anode. In the GM tube. In the GM tube. And now, do we know why it is formed? This is the reason why it is formed. It is formed because of these conditions. When the ions collide, yeah, we experience what we can call secondary ionization. Secondary ionization occurs when these ions formed collide with other gas molecules, yeah, to produce more ions. When they produce more ions, we will have so many electrons that will form what we call an electron cloud or an avalanche of what? Of electrons. Now, to minimize that, because that will affect the results, if you have a very big avalanche of electrons, it can be in position to distort the discharge which is expected to be produced. Now, how do we avoid that? We avoid that by bringing in the halogen vapor, which is a bromine vapor. A halogen is a vapor, or it's a gas which is brought in to absorb the energy of the ions that have been formed by secondary ionization. So a halogen vapor is a gas which is brought into the chamber to absorb the energy of the ions that have been formed by secondary ionization. And with that, we would minimize production of ions by secondary emission. Hence, we shall be in position to control the avalanche that would have been formed by using the halogen vapor. So most of these items you have the write-up, unless if someone has a question to pose here, because you told me to review them. So can I have a question? Someone has one? Actually, Iyo is in which class?
Yeah, I have something to ask.
Yes, please ask.
So, okay, it's connected to this lesson, but outside the lesson, you told us to watch the Chernobyl film. But so which instrument was that which they were using to tell the radiation?
Who? The one which they used to detect at home? At homes or in the factory?
Radiation.
At homes.
Not in the factory, after it had exploded.
Then these women, that woman who detected that radiation was spreading around.
Yes, yes.
I think they had just installed, she was a sensitive radioactive physicist. So she had installed sensors in her house everywhere, whereby when she opens, she had no inlet in her house. She could only inlet after opening the doors and the windows. So when she opened the window, she realized that the radiation started entering, and then the sensor was kicked, was what? The sensor was set off, which was sensing the radiation. So I think she had a sensor in the house that was predicting radioactive particles that could be flying around.
Teacher,
So I don't know the specific
main
material a device she had.
Teacher, what about the men?
There's someone wondering, the girl has even watched the movie, ma'am. Those are the serious students. What about her mother, what?
There are certain other instruments which the men were working with in the area after the explosion. They were holding them in the hand.
I've watched Chernobyl like 2 years ago, and I will need to take a look again and see some. I have it on my laptop. I'll rewatch today, I think, and take a look. Then you'll get back to me in my inbox. Hope you have my WhatsApp line.
Yes, teacher.
Okay. So some of the uses of the GMT, they can ask you to state the uses of the GM tube. One, we can use it to determine half-life of a radioactive sample. And in that case, they can ask you to explain how you can use a GM tube to determine half-life of a radioactive sample. I don't know whether you've made such a question. Those of us who have a question bank and we normally visit it, you must have seen such a question. Have some of you seen it? Have you seen such a question? So you write down the question. Explain how a GM tube can be used to determine half-life of a radioactive sample. So if you want to determine that, we say the solution would be, I'm hoping you're writing this one. One, the radioactive sample is brought close. Yes, please.
Teacher, pardon the question.
Explain how you would use a GM tube to determine the half-life of a radioactive sample. But I can also send, okay, I will send you this one also. Let me just hint on them. Let me just take you through. One, you bring the sample and place it close to the thin mica window of the GM tube. Get the sample and place it close to the thin mica window of the GM tube. And the number of count rates per unit time recorded at different times. And record the number of counts per unit time recorded at different times. That means I will not need to send the writer. Then a graph of count rate against time is plotted. A graph of count rate against time.
Teacher,
Yes, please.
the users are done.
Pardon?
Like we are done listing the users.
No, I just said one of the uses is this.
Okay.
And this use, they can always ask you to explain how it is used to determine the what? The half-life of a radioactive sample. So a graph of count rate against time is plotted. Then the time taken for the half-life for the count rate, not half-life. The time taken for the count rate to fall from N0 to N0 over 2. Time taken for the count rate N0 to fall to N0 over 2 is got, and this is equal to the half-life of the sample. So you get your sample. It's just that I lost power. My lights no longer work. But you get the sample. You bring it close to the thick mica window. Then that sample, of course, is expected to start emitting radioactive particles, and they enter into the chamber, into the GM tube. We have already explained earlier what happens in the GM tube. Right now, this example, this number is always around 4 marks. So you don't even need to draw the diagram. So, unless if they put like 6 marks, then you'll have to go into all those details. But if the marks are 4 or 3, just write as I've written. Then when the sample particles enter the chamber, we know what happens. So we shall get count rates detected. So you measure the count rates per unit time recorded after different times. Then you plot a graph of count rate against time. Then look at the time taken for the count rate to fall from N0, which is the original count rate, to N0 over 2. That time it falls from N0 to N0 over 2 is the time of half-life. And remember, half-life is the time taken for the activity to fall to half its original value, or time taken for the radioactive atoms present to decay to half, or time taken for the count rate to fall to half its original value, as long as you don't define half-life in terms of mass. Okay. The other special bit about this tube, it has a graph which explains what happens. So its graph looks like this. Graph of count rate. Against applied PD. Though the distance AB should be smooth. Okay, let me see if I can do another one. Hope you've seen such a graph. So there is a PD here, which we normally call the threshold PD. So we know this one begins exactly here. This one does not have a threshold. So along, let me call this A, then this B, and this C. So along OA, ionization current increases gradually with an increase in the applied PD. So from the moment the ionizing particles enter the tube, the ionization current or the count rate starts increasing rapidly with increase in PD. And this is because as PD increases, the number of ions accelerated to the respective electrodes also increases. Remember, I told you that when the ionization particles radioactive particles enter the GM tube, they form ion pairs there and then. Then those ion pairs are accelerated to their respective electrodes. But they're accelerated because of the high PD between the anode and the cathode. Now, if the high PD is increasing this way, the PD is increasing, definitely also the number of electrodes ions formed reaching the electrodes is going to increase. So there is a corresponding increase between the PD and the count rate, because count rate comes from a result of the ions produced reaching their respective electrodes. So if the PD increases and these ions reach there very fast, likewise also the count rate will increase at a very high rate. So that is why we have the slope of the graph OA taking on that shape. Now, when they're increasing very fast, recombination of ions takes place, and when recombination of ions takes place, we shall have what we call what? We shall have a formation of more ions. And that means if initially more ions have been formed and they are not able to reach their respective electrodes because of collisions with other ions, then that is when the halogen vapor is introduced and it minimizes those items. So in that case, what happens is the electrodes stop reaching, the ions formed stop reaching their respective electrodes. And if they stop reaching their respective electrodes, what is going to happen? You're going to see that the count rate is not going to increase anymore, and that is within region AB. The reason why the count rate is no longer increasing, even if you increase the PD, it is because there is a lot of recombination of ions that is taking what? Taking place. And at that instant, the region in between A and B, you are not having any more count rate detected. Why? Because recombination is at high gear. So in that case, we can say along AB, ionization current is constant as the PD increases. So there is constant ionization current. Constant ionization current. This is because the PD is high enough to accelerate all ions produce the electrons, and at this instant, there is no recombination of ions. Now, this region is what we call the plateau region. And they normally ask a question, which is like this: explain why. You write down this question. Explain why the GM tube is best operated. I think I've over-exhausted the GM tube today. Explain why the GM tube is best operated using the plateau region or within the plateau region. It is because you can say that in this region, let's have that question written down. Explain why the GM tube is best operated in the plateau region. Have we written the question? So the answer can be this is because the ionization current is a constant. This is because the ionization current is a constant. This is because the ionization current is a constant. As the PD increases. As the PD increases. Therefore, the PD is high enough. The ionization current is constant as the PD increases. So as the PD goes on increasing, it is high enough to accelerate all the ions. As the PD increases, it's high enough to accelerate all the ions produced to the electrodes. It's high enough to accelerate all the ions produced to the electrodes. High enough to accelerate all the ions produced to the electrodes. Therefore, within this region, there is no recombination of ions taking place. There is no recombination of ions taking place. And why are we saying there is no recombination? It's because all the PD is high enough, but the ionization current is constant. And that means the PD becomes so high that all the electrons, all the ions are able to move and reach their respective electrodes. So no ion will remain hanging. All the ions will reach where they're supposed to be without recombination occurring. So no recombination of ions takes place. That is why the GM tube is best to be operated within region 8B. Sometimes they can sketch the graph and then they ask you to explain why should we operate the BM tube best between 8B. Then the last part, which is BC. Along BC, the ionization current increases with any slight increase in the PD. Along BC, the ionization current increases rapidly with a small increase in PD, and the result of this is because now after B, secondary ionization can take place. So when secondary ionization takes place, we shall have an increment in the count rate or an increment in the ionizing current that could be produced. So that is our graph I wanted to share with you, which talks about the GM tube. Another common item is the ionization chamber.
Excuse me, teacher.
Yes, please.
On this graph, in the books we have, the
Hey,
graph
wait.
doesn't start from 0.
I've given you the graph for the ionization chamber. I think I've done that. Sorry. And I had drawn it well. Wait. No, then we have to repeat the whole thing. Let me repeat this explanation. I was explaining for the ionization chamber instead of the, when I drew these two diagrams. It's okay, let's review that. The one for the GM tube does not start from the origin. It has a threshold frequency where it's supposed to start. It starts from here. I think that's what you have, isn't it? So you have here point B, you have here point C, perhaps you have here point D. This is count rate. This is our count rate. And this one is our anode PD or applied PD. I have to take this call. Sorry, I had to take that call. I was explaining the graph of what? Of the ionization chamber rather than the GM tube. For the GM tube, I was wondering why we have a beginning PD yet we don't have a starting PD. For the GM tube, the PD at first between O and A is not high enough to produce any count rate which is detectable. That is why the graph shifts and starts from this PD V0, which is the threshold what? Which is the threshold PD. I don't know what went in my head. I was handling the same exact graph. Then I changed it. This is called the threshold what? PD. Now, that means in the beginning, the applied PD is less than the threshold PD, and thus there is insufficient gas amplification, so no detectable pulses are produced. When we say there is insufficient gas amplification, it means we do not have enough ionization of the gases that propels them, the ions that have been formed, to move to their exact what? Electrodes, as we would have predicted. So in that case, you would see that region OA, we do not have any change in the count rate which is detectable, however much we are increasing the PD, until when we have attained the threshold PD. That is when it is high enough now to accelerate the ions to their respective electrons. So within OA, ions do not reach their respective what? Electrodes. When we reach A, the PD is now sufficient. Now between A and B, the PD is sufficient in a way that any increase in the PD can be in position to produce any detectable count rate. And the more you increase the PD, the more count rate you're going to attain. So in that case, we say along AB, the count rate increases gradually with increase in the PD. This is because the number of ions reaching the electrodes, number of ions reaching electrodes increases with increase in PD. Okay. In that case, when we reach point B, that is between B and C, the count rate there is constant, meaning the ionization current that is produced is constant. And this is because the anode voltage is high enough. Here, the count rate is what? This also is called a plateau region. But in this one, you say the count rate is constant. Why is it constant? It is because all the ions produced within this region, they are able to reach their respective electrodes. All ions produced reach their respective electrodes. You can summarize the graph the way I'm summarizing it also, for your revision to be always effective. Yeah, this is because the anode voltage is high enough to accelerate all the ions produced to their respective electrodes. So no recombination of ions occurs. Yeah, hence the quenching is effective. Now, you will find that what is the quenching? A quenching agent is what we call the halogen vapor. That quenching agent is introduced to absorb the what? The energy of the ions formed by secondary emission. So we have a quenching agent here. Even here we have a quenching agent. So the quenching agent is very effective between A and B and C. It means that we do not produce secondary ions, and thus we don't have what? An avalanche that is going to have a problem with our tube. Now, between C and D, a small increase in the anode, PD, or in the voltage, leads to a rapid increase in the count rate. And this is why, because of production of secondary ions. And the quenching agent is less effective. So in this case, what happens is a small increase in PD brings about a rapid increase in a count rate. Okay, so you can summarize that graph like that. Between OA, what happens? Ions are not able to reach their respective electrodes, reason being the PD is not high enough to make them accelerate to reach their respective what? Electrodes. Then between A and B, there is a quenching agent which has been applied and it is effective, and therefore no ions reach, and therefore when between A and B, more ions are reaching their respective electrodes with the increasing what? PD. And then between B and C, there is a constant count rate being produced. All the electrons, all the ions that are produced are traveling through a PD which is high enough to make sure that all of them reach their respective electrodes. And still, between B and C, there is no secondary ionization experienced as a result of effectiveness of a quenching agent, which is our halogen vapor. Then between C and D, any slight increase in voltage brings about a rapid increase in the count rate as a result of production of secondary ions. Yeah, and in that case, the quenching agent is not effective between C and D. They can also ask you, where is the quenching agent less effective and where is it more effective? It is most effective in the plateau region. The plateau region is the region where we have BC, where the PD is high enough to produce a constant count rate, and at that instant, all the ions produced reach their respective what? Electrodes. I think I've cleared that here. Okay, someone had a hand. I saw a hand. Did someone raise a hand? Marin. Hello? What was it?
Yeah.
Ninakueleza sete kwenye simu kamala okusomesa wano. Yes, Marin. Marin Sima. Marin.
Background count rate is like if they ask you what is background count rate, and then also why must the argon gas be at?
Why must the argon gas be? Hello?
And what is background count?
What is background count rate? Background count rate should be originating from the ions formed as a result of secondary emission. Then the other item you mentioned was, what's your concern? Hello? Hey. Sorry for that. The other question was?
Why must argon gas be at low pressure, and explain background count rate?
Yeah. Now, why the gas has to be at a low pressure? First of all, if the gas is at a high pressure, What do we know about gases in high pressure? If gases are at high pressure, one, in most cases, if the pressure is high, that means the cylinder, the metal cathode cylinder is going to be very small in terms of cross-sectional area, and it means the ions or the electrodes can easily move from one side of the wall to the other side of the wall in a short time, and that means they'll be moving very fast, and thus they'll be having a lot of kinetic energy. So if the pressure is high, then our quenching agent might not be in position to absorb the kinetic energy of the ions formed by secondary emission, because they'll be moving at a very high rate. Are you getting my point? Hello? 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 The person who asked.
Oh, yes, I thought you were talking on phone. I'm hearing.
Then the other one you were mentioning, what about background count rate, is it?
Yes, teacher.
Now, that is what we call the count rate, the number of counts recorded by a radiation detector from background radiation. The number of counts that are recorded by a radiation detector from background radiation. Background radiation can, according to this item, can include what we have called secondary ionization. When we have other ionization coming in from within, yeah, that is what brings about background count rate. So I think we are done. We have exhausted this GM tube. So the two most common items are the GM tube and the ionization chamber, which everyone should be in position to enjoy and discuss whenever they come up. 60. Hello, ndi mu class bado gamba chaje. Mukore nkanda. Ate we mukyalo. Oba mukyalo buze. Kale. Soko kwireko kopeto wile mvuka wali. Wani bale tubumikisi. Ate ero kyankubira kwe mtn. So we want to discuss the ionization chamber. Now, the ionization chamber.
Teacher Hamza.
Yes, please.
You've said we focus more on the GMT and ionization chamber. Does that mean we put?
I did not say that.
On the
I said they are very common questions on this. Why am I saying they are very common? They will ask you everything I've discussed. The other on the diffusion cloud chamber and the expansion cloud chamber, they can just ask for the experiment. But here, they can ask you to use a GM tube to determine half-life. They can ask you to explain where the GM tube is best operated and why. They can ask you to explain why the anode is made of a thin wire. They have a lot of retorting questions about them. That is their difference from the other chambers, which are expansion and diffusion. Yeah. So these are two. They can ask you about one. They can ask you about the thin wire anode. They can ask you about the graph. They can ask you how to use it to predict half-life or to predict activity of a given sample. Yeah. So it's just that these ones can attract more questions, especially of the explanations, than the other two, the expansion and the diffusion. That is what I meant by them being more popular or more common. But I'm not saying that they are the only ones you should put on energy. No. My main point here was to show you that these ones have so many questions that rotate about them. So you need to know most of those small nitty questions that can be said depending on these items. Hope I've differentiated, but refuting what you were
Yes,
saying.
teacher. Yes,
So we can
teacher.
talk about the ionization chamber. Also, this one we are going to expand it, explain it, and exhaust most of those naughty items. I'm going to find some questions and pose them to you so that you can see how best you can answer them. The ionization chamber. Sometimes we draw it like this. Then we bring it here. This is an insulator. We have our radioactive source. If the source is missing, whatever you're doing is garbage. Source of radiation. There is air inside at atmospheric pressure. This is a metal casing acting as the positive electrode. This one is a brass rod acting as a negative electrode. Which is our negative what? Electrode. Now that is one way it can be drawn. No, but this is not the, this is supposed to be a thin wire. Sometimes it's drawn like this. This one is going to be our, this is our cathode. Wait, let me see. Yeah, then this will be our anode. So this is the negative terminal. This is a positive terminal. So this is positive, this is negative. Now, I hope you have such a diagram, either this first one or the second one. Whereby if you have the second one, the reductive source will be placed this way. So this is the sensitive current detector. When we say a sensitive current detector, physics items are sensitive if and only if they are able to measure very small quantities of units they are supposed to measure. That's why this is called, according to this second diagram, this is a micrometer, a mirror ammeter. So if it's a mirror ammeter, that means it measures very small quantities of current. So a device in physics is said to be sensitive if it can detect very small quantities of units it has to measure. So if it can detect very small values of current, then we say it is very sensitive. Now, how to explain? First of all, radiation enters the chamber through the lid. This is called a Papex lid. So radiation enters through the lid and forms ion pairs or ionizes the air inside the chamber and forms ion pairs due to ionization by collision with the gas molecules. So when ion pairs are formed, definitely we say they move to their respective what? Electrodes. Why? Because of the high PD between the anode and the cathode. So the applied PD between the anode and the cathode enables the electrons and the positive ions to move to their respective electrodes. And this causes a current to flow in the external circuit, i.e., ionization current is going to be detected by the amplifier. Therefore, there is presence of radiation that has been detected. And that is as brief as that. Yeah, so for this one, radiation enters through the Papex lid and enters into the chamber. And because of collision of the radiation with the air particles or air molecules which are in there, we form ion pairs. The ion pairs formed move to their respective electrodes. When they move to their respective, I'm going to send you a certain guide. I have a guide here, which has a simple presentation of how it would have been considered when explaining an experiment about an ionization what? Chamber. So I'm going to send you the solution. Actually, I even have the question. Yeah. I'll send you the solution. Oh, this air being at atmospheric pressure, I forgot something here. There is what brings in the air in and out. So air enters through here and through here. That is why we are saying the air is at what? At atmospheric pressure. So therefore, yeah, I'm going to send you this also so that you can have better. But I was saying, when the ionizing radiation enters the chamber, it collides with the air molecules. Ion pairs are produced. When the ion pairs are produced, of course, instead of saying positive ions move to the cathode and then electrons move to the anode, we say the ions produced move to their respective what? Electrodes. And then the current flows into the external circuit, is detected by a sensitive meter. The sensitive meter, one can say by the micrometer. This is the microammeter because of the mu. So one can say it's a micro what? Ammeter. The PD is set to such a value that all ions are collected before they recombine. So that means if you set the PD to a value that all the ions are collected before they recombine, then you will not have recombination of ions. The saturation current produced in this way is the measure of the rate of primary ionization. So I'm going to send you all this and you take more notes and adjust where necessary in your notes. Then we go to the graph. For this one, its graph starts from the origin, with this as the PD applied across the chamber, with this one as ionization current. Actually, the difference between this one and this one, the graph, is that the other one uses count rate, this one uses ionization current. Yeah? So for this one, straight away we shall start from O. The PD increases gradually until we reach saturation. So from O to A, then to B, then to C. So the current here at A is what we call the saturation what? The saturation current, which we shall arrive at. So O and A, what happens between O and A? The PD is not large enough to draw all the electrons and the positive ions to their respective electrodes before some recombination has occurred. Now, what happens is at O, when the PD is applied, straight away we get a pulse detected. So we shall get some ionization current flowing. So, but the PD is not so high enough to cause what? To cause recombination of ions. Then when you reach point A, when you have increased the PD, you will attain what we call the saturation current. And between A and B, what is going to happen is that the PD is going to be large enough as you go on increasing it. But as it is large enough, all the ions are able to reach their respective it's high enough to prevent any recombination. And in that case, if it's high enough to prevent any recombination, it is not so high enough that it produces some secondary ionization. And this ionization current is said to have reached when a value of IS has been attained. So if I come again on that statement, we are saying the PD is large to prevent recombination, but it is not so high. It is not so high that it produces secondary ionization. The ionization current at this instant produced is said to have reached is what we call, it has reached what we call its saturation value. So that's why we are calling this IS, we are calling it saturation what? Saturation current. Then beyond the B, the PD is large enough to cause secondary ionization. The PD at which the ionization chamber is operated should be such that the ionization current has its saturation value. So it means the best also option to operate this chamber is within AB, where the current has reached its saturation what? Saturation value. And this is also called the plateau region. Plateau region where the chamber is best operated. And the reason why it's best operated there, it is because the PD at which the ionization, it is because when the chamber is operated, we do not have recombination of ions at this instant. But we have what we call secondary ionization that is taking place. And when secondary ionization takes place, we end up attaining what we call the saturation current, which is the best value of current to operate the chamber on. So I'm going to send all this right up and review with what you have. Then you have yourselves updated with the best write-ups in these areas. What time is the lesson supposed to end?
10:30.
Are you sure?
10:30.
Okay, then the rest are just the diffusion and expansion cloud chambers. I don't know whether you have much concern there also, but like you've seen, these ones have very strange. And then the other thing is, people draw this diagram wrongly. They confuse this because they have seen in the GMO tube the thin wire anode is in the middle. They also call this one the anode, my friend. Okay, I've drawn it as a thin wire, but it looks like in most books you'll find it like this. Some people draw something as big as this, so that they take it to clearly see that it's a rod, not a wire. Some books draw it as big as that, so that they confirm that this is a brass what? A brass rod, which is our cathode. Those are the differences between this one and the other one. The other one is made of a thin wire anode. This one is made of a what? A cathode rod. They ask you for the differences between the two. We need to have them stated. Okay, with that, let me send the questions and the guide, and then I also send the notes, which I've promised to send. But the question, I'm going to send the guide, but the question, you go to the year 2018. Whoever has that here, please share it in the group so that we can all have this question, and then we have the solution as well to look up to. Share with us 2018, the year of 2018. We need to see how that question set 10 was set. Then I see how people can answer that. Okay, so we can have that called a day. So we shall start from there next time. Who is Nowera? BCMA, they are going for math. They're going for another lesson. Okay.